Okay, I would say we give it a try. Let's get started. Welcome everyone to our workshop, Short Beyond CID. What else is there? I'm very happy to be joined by my colleagues, Valentina, Lukas, and Nicola, and we would like to give you a glimpse. Why do we need technologies beyond CID? What's out there? And we're going to showcase a few things left and right that have been already done to show you what the power of other approaches than CID are. So to give you an overview, I will just start with alternative fragmentation methods, what's out there. Valentina will showcase her work on acyl carnitines and EID. Lukas will go for some photodissociation in here, and Nicola going at the end with breaking annotation barriers, which I guess we are all interested in, how to break bonds and annotation barriers. I would say we directly give it a start, and I will jump into these things. Alternative fragmentation methods, why do we need it? And from the point of view how I got into this topic, actually it started all with lipids, right? So people were always interested in say, PC36-2, what is it, right? We can't do anything biology with that. So where's the double bond, which fatty acids are in there? So we now know that there are technologies like EID where we can locate double bonds, where we can have the SN1, SN2 specificity, and there is actually a poster which I recommend you to check on this. We did this for NIST plasma on the lipids. But it's not only about lipids, right? So the question is now, what's going on with metabolites? So there are examples now, what you can see, and is this thingy? Yeah, kind of working here. So just some typical plant metabolites where we have the flavones, flavonols, and so on. And you see all these numbers. These are all the possible positions where we can have hydroxyl groups. These hydroxyl groups can have modifications like glycosylation. And it's very, very important for the biology to actually know where is the hydroxy group, where is the modification in there. So we want to get more detailed annotations, more detailed identifications. The other side, you can see actually bile acids, just these three isomers, DCA, UDCA, and CDCA, where we have different positions or different stereochemistry of this hydroxyl group in here. So it's really important to differentiate these things. And these are, well, I have to admit, these are easy, these three bile acids, because you can separate them chromatographically, but there might be also novel ones, different ones, where you need actually more information to identify where is the location of an hydroxy group, where is the modification, where is the glycosylation, whatever happening. So it all started with lipids, but metabolites, we basically have exactly the same problems. And I think there's a talk by Paul Baker in the vendor session. He will extensively talk about bile acids and EAD. I guess so, at least I guess so from the talk, Paul. So the question is, why do we need something more than CID? So you all know the CID spectra, and I hope you're all capable of interpreting CID spectra in here. And we typically know that in CID we break the weakest bonds, which are typically ester, amides, and all these things. So we don't get a lot of what we'll say really diagnostic fragments. And I don't know how many of you have done EI, GC, MS, EI, where you get all this peak forest, but you get a lot of structural information out of this. We don't have that in CID. So we actually need alternatives for this. And I already mentioned it, we need alternatives to find the position of double bonds, to need to find the position of hydroxyl groups, glycosylation, and so on, and so on. So the question is, what's out there? And I just summarized a few things by presenting, by looking for alternative methods in here. So there are the electron-based fragmentation methods, there are the photon-based fragmentation method, and something that I call others, which in a strict sense are CID, but there's a kind of a twist in there, and these are emerging technologies. This is why I have added them here, at least for the overview of things. We won't cover them in detail. But I guess we all know how CID works, so we have the excitation of the ions by the collision with a neutral molecule. By this, you are exciting the ions into an excited state. You have the internalization of the energy, and then what's happening, actually the molecule starts to fragment based on the molecule on all the different fragmentation pathways. There are the electron-induced dissociations, and actually they have been around for a while, and they are very big in proteomics, especially structural proteomics, ETD and ECD. And what basically happens, you see ECD, electron capture dissociation, for example. You have an ion which captures an electron, but its capture, you have energy. This energy is again internalized in the molecule, and this leads to fragmentation. And if you now close attention to the formula in here, you see that actually there's a charge N plus. We are typically dealing with single-charged molecules in here, so you can do the math in here. So if you have +1 charge, you add an electron, well, that's the end of the ion, actually, so we won't have any fragmentation, we only have neutralization of the molecules, so no fragmentation actually happens. And what was the secret sauce to go of these things is to raise actually the energy. So we have ECD, we have hot ECD, and there has been the great work from Takeshi Baba on EIEIO, electron impact excitation of organic ions from organics. So the important thing was really to raise the energy, which actually leads to a fragmentation even for single-charged molecules. And this was somehow a game changer now, not only that it got available, because the technology is around since many, many years, and now it got finally also commercialized a few years ago, that we are now having access to these things. The important thing I would like to remember about EIEIO, when I talk to many people, they say, oh, that's like EI. I said, no, not at all, not at these energy levels. This is still a capture type of fragmentation. So it's not like you're hitting with electrons and you have with EI just break the bonds by this. No, it's a capture type of thing. So potentially once we raise the energies, and you see here we're stopping here at this illustration from Sykes currently at 25 electron volts, but if we can go higher, we might reach something that's EI type, but this is an electron capture type of dissociation, just to keep that in mind. So it's not EI, very, very important. The other thing is how you can excite your ions. You can use photons. So you can use, for example, multiple photons in the infrared, or you use, like Lucas will show us, actually some heavy energetic photons in the UV. You have an excited state, and this also leads to fragmentation in here. There are other things. Basically, they are CID, and they are useful for very specific types of questions. For example, oxygen attachment dissociation, where you have the attachment of oxygen radicals to the double bond, which allows you to very easily and very nicely locate double bonds. But this is a very, very specific question, very specific to lipids, for example. And likewise, there's also ozone-induced dissociation, where you do the same thing with ozone. OzID, for example, is commercially available. OzID is something where most people still build their own instruments. You need an ozone generator. You have to introduce the ozone to the collision cell in here. But these are very, very specific questions. So we won't cover them today. Why is it actually important to have such a workshop now? Well, until a few years ago, this was all home-built instruments, right? So there were the mass spec geeks that started, okay, let's put a laser somewhere, let's put something else somewhere, but these things are now commercially available. So there are tons of instruments, not tons of instruments, but instruments available now. So we have, for example, the Orbitrap. I always forget, it's a tribrid ascent, I think. With UVPD, we have the Xenotofs, the 7060, 86 with EAD capability. We have the TIMS Omni, and we also have the Shimatsu QTOF. Sorry if somebody from Shimatsu, I have no idea which number it is, but it has the OID on it. So these things are now available to, I would say, us non-mass spec geeks. Sorry if you're a mass spec geek, please, sorry for that. So they are available, and more people will use it. So we thought it's timely to actually start a discussion where we can use these things, what we can do with it, and maybe to join forces to go on with these things. In this workshop, we basically will cover these two methods. So EIEIO, or what a lot of people just simply call it EAD, or EID, but it's important to see, like collision-induced dissociation, we have electron-induced dissociation, EID, and we have this subtopics or the sub-methods of it. So EIEIO and UVPD are the topics we're going to cover today in this workshop. What's available? Well, there's the Bruker TIMS Omni, and you see actually we have a lot of energy ranges, and somewhere, I hope it's working, hello. We also might reach now the EI type of fragmentation someday. I have to admit this machine is currently biopharma only used. There has been no small molecule use so far, I think a few pharmaceuticals. So far I just want to have it here for completeness, but you see also that here there's the, this thing is amazing, EID type of fragmentations theoretically possible. So over time it might get interesting also for small molecule applications. We of course have the Xenotofs, the two models where we have actually the EAD sorry, you really have to press the button hard because otherwise nothing happens. With the EAD cells, all the QTOF type of instruments, and I think Lucas will talk about the OmniTrap Tribit, where you have actually also here, yeah, use the mouse, yeah, that's, press really hard on the mouse, yeah. Where we have the UVPD module over here, where you can also do photo-based dissociation in here. So just to set the stage, we got a CINOTOF. We were wondering, where is it working? And we reproduced the lipid examples, and yes, it works, actually. So again, go to the poster of Sarah, she's sitting here, and also the work from Nicola, he will show. But we were wondering, where does it help on top, right? So sorry about the vendors in the room. You can kill me afterwards, but the examples you show is always a bit of cherry picking, right? Here it works, and there are some other examples where it doesn't work. So it's really important to identify the examples actually for which type of molecules, for which class of molecules does it work, where do you get more information? And the important thing here is actually more information. I'm not talking about more peaks, I talk about more information. Do these peaks carry actually more information that allows us better annotation? So to set the stage, we started off by building some CID, EAD library on the CINOTOFs, and we started comparing these things. And we are still doing together with Sebastian and Nicola. These are very, very preliminary stuff I'm showing in here. But what you can see, actually, so this is one example in negative mode where we have CID and EAD spectra, where we have actually much, much more peaks for this molecule, N-acetyl aspartic acid, in the EAD. And the question here is really, okay, more peaks, does this translate to more information? So what we did is actually put it into series and checked if it really helps with better identification. So actually, CID was already doing quite well because it's the top hit in there, and you see it actually here. So there's the top hit, and there's something else, and yeah, it's a top hit. But if we go to EAD, what we see actually with the scores, we have much better separation of the first hit and the runner-up. And this is some use case that I could imagine actually for EAD and other alternative fragmentation methods to better differentiate results from different isomers, from different structures, which are potentially in CID very, very close to each other, but EAD might allow to separate these things out. Big fat disclaimer here, Sirius was not built for EAD, but it still does a good job on this. So if you put EAD spectra in Sirius, be aware it has not been optimized for these things, so take it with a fine grain of salt and be on a more careful side of things, please. One thing that surprised us actually is fragmentation of sodium ions, and if you do CID, you probably all know that sodium ions don't give a lot of fragments in here. So what we saw actually with EAD, we get much more fragmentation of sodium ions in EAD. And the question again here is, does it carry information? So we put it again into Sirius, and I think the important plot here is actually the fragmentation. You see a lot of green in there, which means you can actually decompose the structure, you can decompose the formula of the fragment. So this is valuable information. And you see actually here this very deep fragmentation tree of this molecule, biocytine, in here. And actually with EAD, we got much, much better fragmentation in here, much more information. And you see here this fragmentation tree of the CID spectra. And actually what turned out, this one is completely wrong. So in CID, there was not enough information to correctly assign the right formula. So with EAD, we actually have been capable of this. You see, this is a structure that the CID spectrum for the sodium suggested us, so no similarity to biocytine at all. And here, this is the EAD spectra. So there is some added value in here. What we're currently trying to evaluate actually is now, okay, you would argue, okay, I have the fragmentation of the proton adduct. Why do I care about the sodium adduct? So the question is, does the sodium fragmentation actually carry more information on top to the fragmentation of the proton adduct, which allows you structural identification? And people will talk about this in more detail. We'll give you some information. I see Andres is sitting here. He's actually a PhD student doing all these fancy things in here. What about UVPD? I'm not an expert in UVPD, so I just briefly copied this out from the paper of Gerard Hofgartner's group. So you see here very endogenous molecules like cocaine, fentanyl, and so on. And what I got from UVPD, and Lucas, you can correct me or tell about it, It's not like a Swiss Army tool, so you have to tweak it a lot actually to get good results. So you see here, for example, for cocaine, you get additional peaks where, for example, for fentanyl, nothing is happening at all, at least under this condition. So you see actually here the CID, 30 electron volts, and the UVPD with 170 milliseconds irradiation time. So there are also very, very mixed results in here. And this is also true for EAD, so it's not like the Swiss Army knife and let's say, oh, let's EAD everything and we will get the results. No, it's really dependent on the task and what you would like to achieve. And Nicola will talk in his talk about this, that he says CID. Yeah, from the slides, we're looking at that. Yeah. From the slides, I was guessing that at least, how to approach these things. I'm at the end with that from my very short introduction, a bit of shameless self-advertisement. We have the Munich Metabolomics meeting. If you want to know more, Karin is sitting there. She's organizing it. Come around. With that, I'm at the end from my presentation. I don't know how we do it. Shall we have questions now or later? Okay. Okay. Then we do some short questions here.
Are there questions for Michael? We will have plenty of them. Please come to the mic, Jennifer.
Hi, Jennifer.
Hi, great overview. I have a question with your sodium adducts, and I presume you were talking about sodium ions, but I presume you mean sodium adducts.
Yeah.
There's often other adducts other than sodium, so is there actually an overall benefit of being able to fragment sodium adducts?
That's a very good question. So actually what Takeshi Baba did in a lot of his works, actually he was forcing lipids into sodiated versions in here to get actually a lot of information. We built our library where we started off with the standards. We started off with the proton and the sodium adduct. This is the things we have curated, meaning there might be much more potassium and fancy other things in there. We didn't look into them at the moment. So I think there might be advantage, at least from the lipid works, that having the sodiated adduct for some structure elucidation might be beneficial. The question is, if we do our normal LC run, it should be that the sodium adduct, that's the ideal world where you have only a tiny amount of these things. So what you would need to do is just to force it into the sodium adduct, just some post-column infusion of sodium chloride, and I don't want to do that, right? I don't want to clean my mass spec afterwards. So maybe we still need to learn more about this, and like Takeshi did it, he did a lot of sodium things. I have no idea, the SciEx people can tell how often he had to clean his mass spec afterwards, but there might be advantages, but I won't advise you to do this on a routine basis.
Further question? Can you come to the mic, or I come to you?
Whoever is faster.
Whoever is faster. We meet.
Oh, I can't reach the mic.
Jump.
Hi, thank you. That was really nice. Do you find a lot of overlap between the EAD and UVPD spectra? So what's the overlap? How does that look?
We haven't done any UVPD work, so
okay.
Lucas can talk about it. Nicola knows.
My 2 cents are no.
Okay.
They are orthogonal in many cases. Do we have examples today? No, but I can send you some. But they are really orthogonal, and I think that's the beauty of that. That you can combine them, I think, in the long run.
That's really helpful. Thank you very much.
Other questions from Michael?
I'm here all the conference. Just hit me and ask questions. Good. Then next, Valentina is up. She will showcase a few examples about the acyl carnitine. So please, stage is yours.
Okay. Thank you, Michael, for the introduction. I will be talking about the work we've been doing in the last few months about the structural annotation on acyl carnitines using both CID and EAD. So, just to give you a little bit of background, what acyl carnitines are and why are they so important. So, levocarnitine is a naturally occurring compound which is essential for the transportation of fatty acids from the cytosol into the mitochondrial membrane. But this can be done only after attaching it an acyl-CoA group, so transforming into an acyl chain. So after doing that, it can be transported through a carnitine shuttle system using different transporters. So the first one is carnitine palmitoyl transferase, so basically this one, CPT1, which is able to transform the acyl-CoA into an actual acyl carnitine. After that, CACT, it's a second transporter, which actually transports, it's a translocase, transports the acyl carnitines into the mitochondrial membrane, and then CPT2 in the end transforms back the acyl carnitine into the acyl-CoA, and then the beta oxidation can begin. So as you can imagine, this is why transporters are so important, and deficiency in those transporters may lead to a lot of disease. So for example, a deficiency in CPT1, which is a genetic disorder, can lead to fat metabolism problems inside of the mitochondria. Or for example, a deficiency in CACT, which is a rare autosomal recessive disorder, can still impair fat metabolism and can be also a sign of impaired fat metabolism inside of the mitochondria. This is the reason why acyl carnitines can be biomarkers of the impaired fat metabolism inside of the mitochondria. So the question now is, can acyl carnitines serve as a biomarkers? Yes, I already answered to that, but those are a few examples of this. There are many studies studying the correlation of levels of long-chain acyl carnitines or short-chain acyl carnitines to different diseases. For example, heart failure, diabetes, cancer, sepsis, and so on. For example, heart failure is associated with an increased long-chain acyl carnitines. Another example, diabetes is associated with the decreased levels of short-chain acyl carnitines, for example, C3, C5, C6, and so on. Another interesting example is cancer, which is associated with an increased long-chain acyl carnitines together with the decrease of short-chain acyl carnitines. And another important example might be the association of acyl carnitines with inborn errors. For example, valeryl carnitine, which is a 5-chain acyl carnitines, is associated with methylbutyryl CoA dehydrogenase deficiency. Or, for example, CACT deficiency, as I previously said, is associated with a deficiency of long-chain, an increase of long-chain fatty acids, acyl carnitines. So, this is, so why should we consider acyl carnitines fragmentation? If we use CID as usual, we can get some information about acyl carnitines, but mostly from the head. One of the most important fragment, one of the highest fragment we can get is the 144, that basically is the carnitine itself after the loss of water. Or we can get other fragments from the head. For example, a mass to charge ratio of 85, or the 3-methylamine with a mass to charge ratio of 59. But we won't get any information about the acyl chain because it is hardly fragmented if we are using CID. EID, on the other side, is a novel technology which we have been using for the structural elucidation of lipid chain. Here I reported an example. This is saturated backbone. In a saturated backbone, as we can see, we can have a difference in all of the fragments of a mass to charge ratio of 14 because it produces a rich fragmentation. It produces a lot of fragments with a mass to charge ratio of 14 if we don't have any double bonds. I reported an example about the fragmentation of acyl carnitine of a very recent publication, which was published a few months ago in 2025 about the differentiation of 3 very similar isomers: valeryl carnitine, isovaleryl carnitine, and methylbutyryl carnitine. Those are very similar, and the only difference is in their in their branches. Valeryl carnitine is the straight chain, as you can see, is the straight chain carnitine. And if we use EID using a Z0 of 7,600, we can get some fragments. For example, we can get 203, 216, and 230. If we look to the fragmentation spectra of isovaleryl carnitine, we can see that we are missing 1 fragment, 216. Why is this? This is because the fragment 216 is coming from the loss of an AT group, which of course doesn't happen in methyl branches. In methylbutyryl carnitine shows a newest fragment, the 217, which is coming from cleavage exactly at the branching point. So, giving those very interesting results, we wanted to compare the Zeno 7600. Oh, sorry, I forgot to mention that this study was done by using an accumulation time of 1 second, which is kind of a lot. So we wanted to compare Zeno 7600 with the newest brother, Zeno 8600. So we basically used exactly the same condition. We used the same LC, which was basically switched between the 2 instruments. Here I reported all the parameters, but they are in my poster. If you want to check onto the tomorrow's session, it's number 2268. So yeah, we've been running some NIST samples, and here we have the results. So if we compare the results of Zeno 7600, which is highlighted by the red line, you can definitely see that there is a huge difference with Zeno 8600. Those 2 peaks were identified as the 2 5-chain acyl carnitine, the 2 isomers of the valeryl carnitine. And as you can see, for those 2 examples, we have an increase of the signal about 17 and 18-fold using Zeno 8000. But we also detected other acyl carnitines. Using Zeno 8000, we detected 35 acyl carnitines, while using Zeno 7000, we detected 33 acyl carnitines. Even though the numbers are very close, what is really different is the sensitivity of the instrument. Indeed, for all the acyl carnitines, we detected an increase of signal from 5-fold and above. So we moved forward, and we wanted also to see if this increased sensitivity of the instrument was also reflected into an higher quality in the EID spectra. And yes, also in this case, Zeno 8000 gave very interesting results, because we obtained similar results by only using 95 milliseconds of accumulation time instead of 1 second. So we moved forward, and we also wanted to perform a little bit of structural elucidation about some of the long-chain acyl carnitines which were identified. So we compared the EID fragmentation spectra of carnitine with an 18 carbon chain without double bonds. So the first one, with the fragmentation spectra of carnitine with 18 carbon chain with 1 double bond, but in different positions, respectively 9 and 11, and with the same carnitine with 2 double bonds. So, first of all, we always detected an M+H adduct together with the radical. they were identified as acylcarnitine because they are always presenting the two main fragments, which are the 144, which is the carnitine that I showed before, and the 162, which is basically the same carnitine with the water, without losing water. Here we highlighted with the green line some of the most important fragments, which is the loss of carbon dioxide, which is showed by fragment 383 for the carnitine without double bonds, 381 for the one with double bonds, and 389. This is always the loss of CO2. We observed this in all of our analysis, and I mean, it's hard to detect this because it's overlapping with the EAD spectra, but it's always there. And probably the most interesting part is how we localize the double bond. As I showed before, when we don't have any double bonds, there is a mass to charge ratio difference between the fragments of 14. Here we detected the fragment 312, which is a mass difference of 12. So when we had that mass difference of 12, we detected, we were able to assign the position of the double bond. And this is done for all the compounds, as you can see also for the compound with two double bonds, where we had different fragments, 352 instead of 356. So this is the complete table of all the identified acylcarnitines. As I said before, this is also in my poster. If you're very interested, we can also talk about it tomorrow. So in conclusion, Xenotoph 8000 consistently outperformed over the Xeno 7000, especially in EAD modes. For all the acylcarnitine, it showed up 5-fold increased sensitivity of the peak areas, and thanks to this increased sensitivity, we were also able to lower the accumulation time from 1 second to 95 milliseconds. So, thank you, everybody, and I open the stage for the questions.
Thank you, Valentina. Are there questions on acylcarnitines, fragmentation?
Thank you for this presentation. You draw your lipids as trans configuration. And is there the possibility to differentiate trans and cis?
Yeah, there might be. There was a study from Sarah, I think. Yeah, there might be the possibility, especially if you look at the V shape, but we didn't do that with the acylcarnitines, but it might be possible.
Can I give my 2 cents? If you know what you're injecting, then you can show that there's a trend line you can sort of infer. If you have an unknown lipid where the double bond is, it's really hard because this kinetics is not really conserved across different lipids, position, and so on. So that's why in practice, we have not seen that this is really possible unless you really have standard to sort of titrate the exact kinetics of the ratio of different fragments. So it's difficult. Better having chromatography for that. Sorry.
No.
Hi, thanks for the nice talk. This is directly the question that I wanted to make, and that is, you showed these nice examples of localizing the double bond, but do they actually separate in liquid chromatography nicely?
Yeah, sometimes yes. For the two isomers of the acylcarnitines, they...
No, I mean the ones where you really had the double bond shift by one position.
Oh, no, they are overlapping, yeah.
So
no, they are not separating chromatography.
Horrible chimeric spectra then.
Yeah, you mean
in reality?
One?
Don't look at me.
Sorry. So do you think it's like realistic and high throughput that you could separate them at some stage? Like how?
You mean chromatography?
Yes.
If we can, I mean, we couldn't separate it, but we can work on this and we can try. But
I mean, you might be lucky and only one is present and everything is good.
I mean, I don't think we can separate them.
Okay. Thank you.
Hi, I also have a follow-up question regarding the chromatography analysis of the carnitines. So in terms of chain lengths, different chain lengths of carnitines have different polarities. Mm-hmm. So what is your suggestion in using like different columns, or just you use like one single column for analyzing all kinds of azocarnitines?
Well, we only used one column for all the azocarnitines, given that, of course, with the increase of the chain length, it increases the apolarity of the molecule. That's true, but you still have the head of the group, which is a polar one. So, I mean, until C18, it's fine to use only one column. After, maybe I would switch. We didn't try, but yeah, I would say
So you
that.
think the fragmentation efficiency is more important than just chromatographical separation?
It's not that it's more important. I mean, you can get some information about the retention time, of course, but you can, I mean, if you know what you are injecting and you use a different column, you can only focus on the fragmentation if you already know what you are injecting. It depends on what you're looking for in your compounds, I guess.
Okay, thank you.
Just one more question there.
My deep past, when I first started separating fatty acids, it was on TLC plates impregnated with silver. So it separates monounsaturated from di. But if you really push it, you can actually separate cis and trans.
Okay.
And I don't know whether you can do that in the gas phase with silver.
I don't know either, to be honest.
Yeah.
I don't know.
Yeah. Just, it's worth trying.
Okay, thanks for the suggestion.
No further questions? Well then, please join me again in thanking Valentina.
Thank you. So,
And the floor is all yours.
Hello everyone. That's me. So my name is Luca Schneider. Nice to meet you. So I'm going to talk about photodissociation as a tool. We actually got a new instrument like a year and a half ago. So since then, I was able to play with that and do some spectra and I would like to share something with you. So is it the photodissociation a relatively new tool? I will answer that quite quickly. And then I will just go through spectra and spectra and spectra, and then in the end there will be more spectra. So I hope you will not get definitely bored, but I will try to show you the differences between the CID, HCD, and the UVPD, and just measured. So the answer to is the photodissociation new? The answer is no. Actually, I found a paper like 50 years ago, almost 50 years ago. They already experimented with this laser dissociation. They were using the infrared laser to ionize the ether, the ether molecules, but it wasn't actually connected to the mass spec, but it was connected to the ICR. So technically, this part of the instrumentation is still going on, and it's just plugged to the new instruments. If you look at the differences between the CID and the photodissociation, you can actually see that there is both pulsed and continuous waves lasers. So with the infrared photons, you have a multiple photons just stacking the energy and causing the fragments, which is actually quite similar to the collisional to the CID, to the collisional activation. But with the UV lasers, which are actually higher energy, you actually put a lot of energy at once, so you can actually see it from the laser wavelength. So those 50 years ago, they were using this CO2 laser, which is quite just 0.2 electron volts per photon. But now they moved to ultraviolet lasers, which now, if you think about, let's say, 157 nanometers, it's getting 7.9 electrovolts. I think in the commercial instruments, they're using this 213, if I'm correct, which is actually overlapping with the double bond of CC and CN. Last year, there was actually a group from Pepatsvachka. I actually saw quite kind of a lot of people from this group sitting here in this room. They did actually a very nice job. So if you want to know something more in detail about the fragments and how everything is going with the UVPD, just go to this paper or ask someone who is still, I can see actually, Vlaďa Vrkoslav sitting there. So what they propose is that during this photochemical cyclization, that between the cathode group and the carboxyl group is creating a ring, which is then unfolded into the cation, and then it's followed again and falls into two parts, which actually correspond to those two fatty acids from the wax ester. They're using the lithium in a mobile phases or in injections, which it should actually enhance the sensitivity, because one of the tricky part of the photoionization is actually that the energy for the molecules is not so very high, so you need to use a very long activation energies. So, every bit of intensity you can actually get into the instrument is very important. So, as I mentioned, we bought this new instrument, Orbitep Ascent, where they're using this UVPD laser. As I mentioned, it's 213 nanometers. It's positioned back in the instrument that the laser is actually going through the dual pressure linear trap, and that's actually a bit of a tricky part when you tune the laser. It took me some time to figure it out that the most important part of the UVPD here at the Ascent is actually really tuning your laser well. And why is it so difficult is that in the back, sorry, I will just go back. So you have here like 4 micro screws, they're actually holding 2 mirrors, and you're trying to position those 2 mirrors that the laser beam is going directly through the both cells, and also it's not like even above or below the stream of the ions. So it's not so easy. I mean, this is so far best I could go. So if anyone can get better results, I'm happy to buy him a beer, and he can tell me how they did it. But the funny thing is that you actually going into one way with the micro screws, and the intensity is going up, and at some point it starts going down. So you're trying to balance those 2 mirrors to actually get really high efficiency. But if you look at the UVPD efficiency here, that the range is okay with 0.25, I would say definitely no. You need to go at least 0.5. Otherwise, the laser is not enough efficiency, and you will have actually quite a low yield of fragments from your molecule. Okay, so now that was a bit of a theory. So now let's move to the spectra. I will start with the histidine as an example of a polymetabolite. Histidine is just, I like histidine, there is no particular reason why, but it's actually interesting amino acid. So if you look at the MS1 spectrum, this was done by the direct injection. You can obviously see the M plus H ion, and then there are some in-source fragments which are actually present always. And getting just the untargeted metabolomics and lipidomics more complicated. If I compare it to the CID spectrum, and I should actually mention that within the thermal instruments there is those difference between the CID and HCD, because in the CID you're technically applying a resonance frequency which is corresponding to the M over Z, and the molecules just start vibrating and moving around, and it just breaks. So which means that after when it breaks, the resonant frequency is now actually active for the fragments, so you get actually just, as it just breaks when the molecule is most fragile, and there is no secondary or tertiary fragmentation happening. So that's why if you compare this MS1 spectrum with the in-source fragments, it's actually very similar to the CID MS2 spectra, which you have from the Orbitep instruments. Also, if you look at the energy, it's actually quite low. I'm just using like 25, which is the normalized collision energy. And if you go higher, you can go, I don't know, I think like 70, there will be no changes actually, not very big ones, because just for the reason that the resonance frequency is not applying for the fragments. So again, it's interesting, but it doesn't give you much information about the structure. So you need to go for the different fragmentation techniques. So that brings me to the HCD, which is technically the CID, what normally understands with the other vendors and the other instruments, just using the higher energy, so the molecules are actually bouncing much faster. It's like shooting a projectile into the helium or nitrogen cloud. And you start seeing obviously the main fragment from the histidine, but when you focus on the lower abundance fragments, you actually start annotating different ones. So far, I'm using a mass frontier for the annotation of fragments, but there are many, variable tools we can actually use. As Sirius was mentioned, there is a lot of open source. So, feel free to use whatever you want, just, to be sure, confident, and have actually nice spectra, which are giving you a lot of information. So, if you compare the HCD spectrum now to the UVPD spectrum, which is measured, you can actually see that for these small molecules and the polymetabolites, it's actually quite similar. So if I just match, if I just match the fragments, you can actually getting almost the same information from the HCD fragmentation as well from the UVPD fragmentation. Just the difference is that with the HCD, I was using quite nice mellow energy around 35 because I still like to see the parent ion even if it's very low. The UVPD is something like 500 milliseconds to actually get a decent fragmentation spectra. But the information is more or less the same. The difference for this is just the ratio of the fragments. So I would say that if you go really high with the HCD energy, you can actually cause a lot of secondary and tertiary fragmentations, which means that you're technically breaking the bigger fragments into the smaller and smaller pieces, that in the end you just have a little bunch of fragments here, which is not very informative. So that's there are other ways how to actually tune your energy to avoid that. But you can see that with the UVPD, you don't have to worry about this because even if you go much higher, I mean the upper limitation is around 1 second of activation time. So even with the 1 second, the spectrum will not change much. Okay, so that was the example of the polymetabolites. I guess there will be also exceptions as well because it's a very broad family of molecules. So I guess everyone can actually find something different. So if I move to the lipids, where I actually think that the UVPD is more helpful, let me start with the separation. I did some separation of human plasma on C30 column, and I had these two nice lipids. With the M/Z 782 and M/Z 780. So I guess you can already tell that there is a difference of 1 double bond from them. If I look at the spectra of the 780, compare the UVPD to the HCD spectrum in a positive mode, this is actually important to mention that it's in positive mode, you see that the parent ion is actually still high and you have just a few low intensity fragments there. But you have quite a lot of fragments. If I use the same energy in the HCD, which I use for the histidine, which is D35, you can see that actually the spectrum in a positive is not very informative there, because the only thing you can actually, which will give you the information is that the lipid is actually phosphocholine, because you can see this 184, and those other fragments are not very informative. That doesn't necessarily mean that if you go to the HCD in the negative mode, which then actually gives you quite nice fatty acid chains, so you can start building the idea about the chain lengths. But let's go back to the UVPD spectrum. So if you look, if you zoom in closer, this region, which is around this 440 to 800, you can actually see there is a pattern of fragments going from the UVPD. And using the mass frontier, and it's a bit of a back and forth football playing, that you actually feed the mass frontier a structure which you're assuming is corresponding to the spectra, and then trying to match it back and forth. And at some point you might get lucky, and you actually everything fits together. And this is actually this case. So when I got this fragment and start checking the spectra, we actually start seeing that all these like envelope here is actually corresponding to the breakage of the double bond before let's say before the double bond. But also you can start seeing that there are fragments which are actually 12 different. So we have these corresponding groups of 684, 672, 634, 644. So these are like specific patterns. And also this corresponds to these double bonds there. But then it's slight different change. So because then it breaks here. And you can start seeing different patterns, which is the 592. And also, I guess this 12 losses, the breakage is somewhere around like here, as was suggested in a publication from my colleagues from Czech Academy Science. But honestly, so far it's like difficult to figure it out what's the precise mechanisms there. But it looks like that UVPD laser is technically breaking the double bonds as well as around it. So you can, depends on the intensity of your parent ion, you're actually getting a lot of fragments around that. And this is probably how it's like corresponding to these. And the last fragment, which is actually interesting, you get a structure of lysophosphocholine 16-0, which is corresponding to this 496, and you have a volt loss to there. So technically, from MS2 spectra, you can actually get a nice structure elucidation of your lipid. If I look at the second lipid, the 7A2, they're obviously quite similar. And if I zoom again to this region, which is actually these UVPD patterns, and compare it to the lipid before, you can actually see that a lot of these peaks are corresponding. Plus, you have this special one, this 724, which is corresponding to the fifth double bond there. And then it actually makes it nice specific. So if we compare those two those two lipids together, we can actually say the position of the double bond on the chain, and we can also say that the other chain is without the double bonds. It's corresponding to the lysophosphocholine 16-0. So it gives you actually the information about the double bonds in the structure, and that's actually helpful because both with the HCD and CID you can't get this information. Okay, so that's just the summary. I'm always like to look at the chromatography at the end because it always confirms your if you're right or wrong. So this more unsaturated lipids should elute earlier because the molecule is more packed, which is actually the case here, and so that's good. Let's focus on the isomer of this 782. So if you can see, there's a little peak down there, so which is going around like 1 minute earlier. So I was also trying to do the structural elucidation of this peak. You can see that the intensity is actually much lower, and this might pose a problem. So if we look at the spectrum, the spectra again, you know, they are diisomers, it's UVPD, so the fragments are not very intense, so you have to zoom. And that's actually starting to be a little bit of a problem. So if you look at the spectra, there are again quite similar fragments, which those two corresponding to the 14 double bond, also this 562 fragment, and there is a difference. There is no 496 as a lyso-PC8, but there is this fragment of 520, which corresponds again to the lysophosphocholine 18-2. And again, they are going in a pair, so you have this loss of water there. So you can actually confirm. But if you want to determine where actually the double bonds on this lysophosphocholine 18-2 are, you can see that the intensity of the rest of the peaks is actually quite low. So these informative peaks are missing there. So in the end, you just actually can say that probably the isomeric lipid will be 18-2, but you're not sure about the double bond position because you're lacking actually the intense enough fragments in the spectra to do the proper annotation. So that's actually that you're running into the limitations that the laser and the instrument is not strong enough, if I say like this. And the fragments, if you go lower at the intensity of the parent ion, actually the fragments are super low and they cannot be detained. So that's actually posing a problem if you're running a chromatography and let's say you have some interesting lipids which will be quite low abundant and you really want to do the structural elucidation on them, then the UVPD might be a little bit of a problem because you will be lacking actually the informative fragments on them. So as would Rick from Citadel say, more lasers. We need more lasers. So if I compare it again, just to summarize these double bonds. So from the first spectrum, which was actually quite nicely intense, we had a lot of informative fragments. So we were able to annotate and make the double bonds position. But with the isomeric compound, we actually were unable to do that. We know about this fragment is 684, but there is actually missing those other ones. So that's actually difficult to say if this like 644, if there is really a double bond, or where is the position of the second bond on this chain, because this is actually missing in the spectrum. So at the summary, to summarize everything, this, as I mentioned before, this photodissociation strongly depends on the supply of the energy, which means it's the electron and activation time. Again, you can ramp up to 1 second, so which means that when you're running, let's say, an LC run, it's difficult to do enough MS spectra on it, but you can, balance it and play with it a little bit. That the UVPD and HCD fragmentation spectra for polar metabolites are actually quite similar. So there is a debatable if it's useful to use the UVPD fragmentation for the HCD, before HCD, but definitely there are differences between the UVPD and HCD spectra. So especially for the more unsaturated lipids. So which means there's a take-home message. I would say that the UVPD fragmentation is really suitable for lipid structure annotations. At least you will know the double bond position. The cis and trans will be obviously more difficult, but then we have chromatography, which can actually solve it in the end nicely. And in my opinion, I think still the best, the combining of the CID, HCD, and UVPD spectra together is actually really good for the structural elucidation, because you have a lot of pieces of information that can actually fit together. And if everything fits together, you can actually be sure, fairly sure that the compound you annotated is the one you want. And that's it. So I would like to thank you to my students, which are somewhere there sleeping probably, or something like this, but I will wake them. And thank you very much for your attention. And if you have questions, I'm happy to answer them.
Thank you, Lukas. Who are the students? Question, please stand up, just go to the mic.
Yeah, Jennifer, hi.
So I have two, if I'm permitted. The first is, I think it was the phosphocholine you showed that you could see the head group on the HCD. Can you see the head group on the UVPD?
Nope.
Okay, so that's why you're recommending combining. And the second is more a comment or an idea. Has anybody tried infusing a photosensitizer, like, for example, riboflavin in the UVPD chamber and see how that improves sensitivity?
I'm not aware of that. Maybe, the laser sits in the back of the ascend. I guess that there will be probably increasing the pressure in a linear ion traps, so I'm increasing the fragmentation, but maybe it's a way. But if you're using the instrument also for other other purposes like proteomics, or just want to do different settings, that actually might pose a problem of extensive fragmentation in the cell, but it's definitely interesting idea.
I was thinking of something that you could switch on and off, but I'll leave you with the idea.
Yeah, okay, thanks.
Just a second. Brendan, you have an answer to the question, or you have another question? Because you might know the answer.
We haven't done any sensitizer
okay, sorry.
work,
but
good question.
I was curious what the chromophore is for the photons in the lipid, and how does that affect the fragmentation differences?
So this is, as I mentioned, the laser is 213 nanometers, and this is overlap with the absorbance of C double bond C and C double bond N, and that's just resonate and then fragments. So that's so there is not really like a
the example you showed had similar numbers of double bonds.
Yeah.
Do you have any thoughts to what is causing the difference in the fragmentation efficiencies and the fragments you're getting, since you have equal number of chromophores?
Well, that's a good question. I don't really know. I was actually happy to see that there is a difference, that you can, if you put those lipids together, that you can see that the patterns corresponding to the structures are actually the same, and you have this additional group of this 724, which I was actually showing. So if I go quickly back, yeah. here. So you have this pattern, which is actually exclusive for the other double bonds. So I guess if there will be a longer chain, there will be another double bonds and another group of fragments there. So is that answering your question a bit?
Yeah, I can ask more.
Yeah, we can chat later. Yeah,
Thank
sure.
you.
Thanks.
So, do you make any use of the MSN capabilities on your instrument? Do you try mixing and matching different fragmentation types at different levels?
Yes, I actually love to combine everything together. The only sad thing now is that you can't do multiple. Well, I remember that in old days there was on Elite that you can do like polarity switching in one method on the ion trap. So you were able to just, pass ions back and forth. But obviously, doing multiple CIDs is actually beneficial if you study, let's say, like metabolites or some drug metabolization, because you're basically cutting off parts of the molecules, and from the bottom up, you can actually build a structure. With the HCD, yes, as well, if you depends, but you have to tune the energies very carefully just to not to over-fragment everything. Combining the UVPD for the MS3 and GON is a little bit more trickier because there is a huge loss of sensitivity between those two. So technically doing the MS3 on let's say, fatty acid chain from MS2 is almost impossible. I tried that, and you need really huge intensities at the beginning. So that's probably a no-go, but you can tune the instrument and maybe one day it will be working, but yeah.
I might suggest trying CID followed by UVPD. It might not be the double bond positions on the side chain, but I think you can get some SN1 and SN2 information because there's a fragment that tends to cyclize after you've lost one of the fatty acid chains or after the head group's fallen off. So yeah, we've got some collateral on that if you'd like to.
Yeah, okay, thanks.
So is that something that will be already MS cubed like, or you do CID first and then UVPD on top? Oh.
Yeah, so UVPD MS to the third can give you SN1, SN2 position. Basically, after the head group's fallen off, the SN3 position cyclizes and forms a ring structure that absorbs the UV light. We've got some collateral on that if you'd like to know more.
Yeah, that sounds great, thanks.
I have a question, not for you, for him. We always see the precursor. You have to zoom in, right, to see the cool peaks for the double bonds. Yeah. So what is it roughly, the yield, is it 1 second, or if you go longer, do you see more? Can you comment on this?
Yeah, so here actually you see that 650 seconds, and as I mentioned, it's about the tuning the laser. This is how really the MS2 spectrum looks like. So you have still like E to the 8 intensity, but the fragments are actually 100 times lower if you go there. So yeah, that's the problem with the UVPD at the instrument right now. And if you actually not tuning your instrument well, you lose a lot of fragments there. So it's really about the position when it's going through the cell.
So do you have any sense on how much you have to inject in terms of concentration of phospholipids to be able to see the guys down there?
Well, I went, so this is from the LC run, so it's just 2 microliters of plasma I injected on the column. But with the direct injections, I went really, really high from the millimoles because I want to have this nice spectra.
Yeah, and that's good for a paper. But if the question is how realistically does it work if you have an average sample? How frequently you can actually spot those double bonds in things you can detect?
I'm not sure about the concentrations exactly, but talking about the relative intensities, you really have to go and orbit web speaking like at least E6, E7. Otherwise, you just don't have these fragments there. It will be ending like the lipid I was looking at the last, that you're actually missing the informative fragments you need for the double positions there.
Thank you. Any further questions? If not, thank you, Lukas.
Thank you.
Nicola. So I want to cover 2 things, and we have time, and I will not, One is what we learned from trying to annotate, I call it EID. I don't think I know enough about the mechanism. That's why I usually use EXD or EID to just say we use electrons to fragment. But whether it's EI, EIO, something else, I leave this to the chemist. I don't know. I just see the spectrum, and I try to make sense of that. So, but we had the pleasure to have one of these instruments, commercial ones, that has this capability for many years now, for 3 years. And we said, oh yeah, cool, there's information there. So let's try to automatize everything. So not running standards, but running real samples and then inferring double bonds, SN1, SN2, all of that automatically. So the idea was, let's use this to quickly learn how to process data, and then we're gonna move to all over the type of compounds. So I'm not a lipidomics person. We were doing this here to learn how to use the data, but the goal is really to be able to use these techniques on a larger broad of things. It turns out it's much more difficult to anticipate it, so I'm going to share with you the problems. I think we sorted out now, otherwise it wouldn't be here. But it's thinking of now expanding this to any other type of molecule, exposome metabolite. I think it's something good that might be good to reflect on. And moving forward is, we want to embed UVPD, all the type of things. How are we going to do that? So I'm trying mostly to launch a discussion, and if anyone interested, also in contributing by whatever mean, let us know, because we really need to join forces on that. We also have UVPD since many years in the lab. We just didn't do enough with it. I'm sorry, it was really our fault. But that would be an option. Okay, so I push on the mouse very strongly. So I start from the basics. And the basics is this paper that was with Campbell and Baba, which I always show. This is nice figures to put in a paper, right? Where everything makes sense. So they inject something, they know what it is. It's a lyso, a phosphocholine, 18-1. Then there's a double bond disposition. And since it's not been shown before, I show this again. I mean, Valentina covered that. But so you get your classical 184. And then the beauty of that is you start seeing fragments between the C1 and C2, or C2, C3. You start seeing that the fragments there. And they tell you whether, the chain that comes off when the fragments here is in position 1 or 2. That's where you basically get that information. And that's a fragment that it's already tiny compared to 184, but it's there. So that's where you start getting this positional information, basically radioisomers about the position. And with lyso or with phosphocholine, so glycophospholipids, it's good because you can distinguish 1 and 2. For triglycerides, you cannot distinguish 1 and 3, but 2 from the others. Basically because you break, the fragment comes off with 1 carbon, and then you have this CH2 on top. So those guys are there, who are fantastic. And then you have the classical, I call it ladder. I don't know if it's where you have all of this series of fragments in the acyl chain. And Valentina described that. You start from a minus CH3, so minus 15, and then you have this series of 14, 14, 14. If it's saturated, if you have a double bond, you have then 2 jumps where it's 13 and 13, because you lose a CH and a CH, and then it goes on with 14. So you don't see this here, but what happens is at 14, 14, 14, double bond, you have 13, 13, but then what happens is that at the double bond, somehow the yield is not so high. So that fragment is hard to be seen. What you have on top is, and this is all described in the literature. I mean, I'm not, I'm just repeating what others observed, the experts. You might have, though, that this double bond here stabilizes some other radicals. These are radicals fragment. So what you see is typically what is described as a V shape, where the neighboring fragments are much higher. And typically, the guy that is with 13 Dalton is not visible, because that's where it's a double bond. The yield is much lower. What you also have in these plots usually is that you have a scaling, which is hidden there. In this case, they scaled up this region by 60-fold to just make it visible. It goes back to what Lucas was showing. The precursor is still here, very large. You have the good, nice diagnostic fragments are there. But then if you want to get radioisomers, are low. If you want to get double bond assignment, it's even lower. And what you see is still sort of noisy. So I think it's cool, it's great. The information is there. For us, the question was, can we now sort of automatize this? Because we are running samples, we don't know what the answer is. Also, I have to say this was a standard, and typically these spectra are acquired over minutes, so 10 to 20 minutes with direct infusion. So a lot of collection time, and that's what you get. Fantastic paper. but does it work in practice? Because we are using chromatography, our peaks are 1 second. So, does it work time scale and k-atomatized annotation? Meaning that if you provide spectrum, can we identify with a double bond is? And we'll focus mostly on that part and all the things that went wrong, and sort of trying to make sense of that. Good. So it works at time scale. There's a pre-print out, actually stuff we have done 2-3 years ago. Bottom line is, and this is with the previous generation of instruments, 30 milliseconds of, it's basically of what they call the reaction time. Basically 35 milliseconds of measurements are enough to get head group, SN1, SN2, and so on. That's the easy part. And we were injecting 200 picogram, and majority of the things we're looking at, there's a preprint is not so relevant. The question is really, how do we identify all of these guys? So this part we identified, and then we need a way giving a spectrum to identify where it is. So we started off with what metabolomics person would do, taking knowledge from the papers and transferring this into rules, kind of rule-based fragmentation, something like that. Because we didn't have any libraries, we didn't have any serious that could do all of that and so on. So, and that's really that comes from the same paper, and it's basically described that every CC bond generates this homolytic, blah, blah, blah. We take this knowledge and we can transfer this in something that is machine readable. And there is this, nothing we invented, it's out there. The cheminformatics community has provided so many tools where you can code them in smarts. And you can think of having then every smile, every lipid, you can just have this guy that tells if whenever you have something like this, you can break it. That's basically the homolytic thing. And the complication of that, if you want to try this at home, is that explicitly whenever you do this, it doesn't like radicals. So it always sort of, works with the even number of electrons and so on. So if you want to start modeling what I showed you before, you have to explicitly put the hydrogens or omit them, and then it's gonna give you the right things. We learned that too. So we did this, basically we set up this rule for the homolytic, heterolytic, all of that is basically express this, and we started simulating the spectra, meaning that you can have every lipids coming in, we can get structures we just need smiles, we can even generate those automatically, smiles, and then we apply this library, and this is now one of this fragmentation of the head group, it becomes larger, but long story short, for any structure, you can generate those theoretical fragments based on that rule. It can be done in millions of things. It is slow, but you just do it once and you get your spectrum. So what we get is for any molecule to start with, any structure, we're literally getting the full list of all of the fragments with M over Z and full smiles for all of things, for homolytic, heterolytic, and so on. So we thought, now we can simulate the spectra, and now let's use this simulation to annotate what we get from the mass spec. It turns out that it doesn't work for a few reasons. Okay, Smart's law already said, and there's a few topics that I'm going to touch, and I think by now we solved. But these are the kind of things you have to keep in mind if you want to go into different type of molecules. One aspect is the centroiding is critical. We are dealing with super small intensity fragments, and they're close to the detection limit of the instrument. Orbitrap is cleaner. With FT, we've used time of flight. Down there, it's a mess. So being able to discern what is a real fragment, chemical, entity from noise on the things is absolutely crucial. If you don't do it, it's not going to work that well. So I'll show you a few examples. The other thing that I'll show probably is that you cannot run this type of things you're doing and try to annotate at the same time the class, SN1, and then the double bonds. So we ended up doing something hierarchical. First, you determine the class, then you determine isomerism if you can, and only in a later point you start assigning double bonds. We can also do oxidation these days, but it must be hierarchical. So one step, and the main reason is that the metrics we use to do this annotation are very different. In one case, you have the big diagnostic fragments, so you focus on those. If you look at acyl chains, it's most of the crowdsourced type of information. It's about the pattern. It's not about specific things. And sometimes even the feature that is missing, right, at the double bond is the one that tells you that probably the bond is there. So we have to use very different type of metrics to solve these problems. That's how we sort of split it up. And I'll show you, spectra are much more complex than what we see in the papers. Although if you read the papers, everything is listed there. You know, all I'm showing now, it's there. Experts know that. But you obviously you have a lot of hydrogen transfers and a few other things I'm going to show you. So, centroiding. Okay, so this is a EAD spectrum. We still have a lot of precursors, you know, because that was done pretty fast. And now we zoom in this region where there is literally nothing if you look at the spectrum. And we zoom in, and that's the zoo of fragments we get. I can tell you, all of the fragments are annotated double bond. But you really have to take something that you typically don't look at. I love to look at log scale plots, because usually that's how we see those. But we basically had to re-engineer or redesign to a large extent centroiding to get much better results. Or put it differently, we were using what the vendor spits out as a, you know, with ProtoWizard, what they provide, and it was not so satisfactory. And then you start looking, okay, but why are we not matching these fragments and so on? It turns out that they're just not so good down there. So long story short, check the centroiding. I'm not saying everything is wrong, but I can say if you check and double check at least once, you might see that you can improve it, and for us it was a game changer. And what I'm going to show you, it works because of this. So, centroiding. Other things, spectrum more complex. So, okay, what you get is, this is log plot. So precursor, it's a LISO 17.0, deuterated, doesn't really matter. You get 184, a few other fragments. You have more fragments that you would expect to see. What you also start to seeing, although we don't really exploit them, but that's going to be the next step, you start seeing also doubly charged things. So they have their own charge, and then, you know, shooting with basically electrons, you start getting radical cations on an SL chain, so you end up having doubly charged, and that's why you end up having something down there. We tend to hide them under the carpet right now, so people just focus on these parts showing this. We do the same, but there might be information down there. But one important aspect is that if you start looking at real samples, you deal a lot, you know, this is 1, 2, 3 orders of magnitude, you have to deal with the noise. So you have to start accounting for things that might be more complex and so on. I'll show you real examples. What is important is the energy, and it was already mentioned, I mean, like it was mentioned, UVPD, you can just wait long and nothing goes wrong, you just get more yields. With electrons, it's not like that. I'm showing this example. This is for the case of lipids. Again, you know, what is the right energy to get best results? If you're too low, you don't see anything. I mean, we just scale this to have exactly the same y-axis. So too low, you don't really see much. That's where the double bond would be. We are just putting all of the fragments, so it would be the -15 and so on. That's the LISO. No, it's not the LISO. 522, yeah. So 18.1 with double bond position 9. Then you go higher, you start seeing more fragments. You go to 12 volt, you start seeing getting better yields. And I'm not showing everything because there's not space on the slide, but if you go higher, then you start losing a lot of that. So for every class of compounds, there's sort of a sweet spot of energy. If you go high, you start over-fragmenting. Something else that is occurring is that you start seeing a lot of rearrangements. And in this case, it's hydrogen rearrangements. So the theoretical fragments that people describe in the papers are those homolytic, where you have a bond, it's split, and everyone takes basically an electron, and that's it. Some of the times, there's a guy which is more eager to steal some of the stuff. There's also basically hydrogens flying around. So if you go with a certain energy, and actually already 12, that is what we use to have sufficient yields, right? Because that's where we get the highest yields. That's where we can potentially also be able to associate or annotate lipids that are not so high in abundance. We need to have those fragments visible. So that's why we move around 12 and 25. This is too low, this is too high, but already here you start seeing not just gray bars, you see these light blue bars, it's where you have an hydrogen, not an hydrogen, actually an hydrogen, sorry, that was lost. So we have 1 Dalton shift. And next to the double bond, you even have one that is 2 Dalton apart. And if you go higher, you start seeing other things where there's a gain. So you see a lot of these sort of hydrogen transfers. Why they're relevant? Well, if you now think that the notation is based on the fact that you have these intervals of 14, 14, 14, 13, 13, Now all of a sudden you have a fragment that gives you ±1, even ±2. It confuses totally this pattern. So you have many more of this +13, or even, when basically there's no double bond, just because of these things. That's why, one of the big lessons was they're unavoidable. We know they are there, but if you go down with the energy, you will not see any fragments. That's why, to keep the balance between being able to see the fragments, you have to start accounting for those. It's not difficult, but it's something you have to account for somehow. Good. How was it done? Excuse me. These are, for example, of real spectra. And I tell you, if you have one double bond, it's simple. The problem is if you start having polyunsaturated, chains and so on. That's what we measure. The label is small, doesn't really matter. But these are basically compounds. These are standards. We inject it, chromatography. And the double bond is here, and you see this V shape I was mentioning. And you already have a shift and so on. And then next to the ester bond, the head group, you start having the oxygen stabilizing some of these radicals, so you have high intensity. But this is the pattern that is described in the literature. For one double bond, we see it. In this case, for the lyso-PC, we sort of see it. We start having interference for other things. We are so close to the baseline that we might start having other things. It's common. I mean, I was basically saying that these are not the big guys. Now, if you start having something with 4 and 6 double bonds, you lose this pattern. And the problem is that we know fairly well how to model a single bond, but it's really hard to see how they interact if you have 2 bonds in the same chain. We don't really have a lot of, we're trying to do that really hard with standards, but the interaction of multiple double bonds of an oxygen in the chain, it's so far very hard to model. And what I'm not saying here, but basically implying is that it would be great to be able to predict the intensities of the fragments. We don't really there because we know how to do it for one double bond, but for multiple, it's basically we are so far. Any help in that direction might be more than welcome. But it's difficult because one is simple, but they're not isolated. These complex molecules, several double bonds. That's why it becomes more. So that's why we had to change the metrics. We started off using the classical matching scores where we pretended we know what the intensities are. In fact, we don't really know. We know for these guys, but for the challenging ones, we really want to use this technology. That's where we struggle. That's why we ended up having a metric which is mostly counting the presence, and the role of the intensity is actually very minor. There's a lot can be improved, but yeah. That's the real data, so that's our library. And again, it's not using smarts, because with the smarts, you cannot actually predict intensity. It will just say what it is. It's literally me and students sitting down in front of the spectra, coming up with a heuristic something. This is the one model for a single bond, which is basically the one we use. For multiple bonds, this is basically what we predict. And what you have blue here and green here is the part that is really matched. So long story short, if you take this spectrum and we run through the entire library, and I'm going to tell you in a second what it is, we get the right double bonds assigned, which is sort of black magic, but it works, and that's where we are. For 6 double bond is the same. So if you take this spectrum, which is very noisy, and I run against not just the right guy, but all 5,065 isomers. So what we do is we take 20 cis exchange, we generate the entire zoo of isomers with all double bond positions. We don't even assume that it can be only omega 3, 6, and 9. The only thing we assume is there cannot be any consecutive double bonds. But then we just run the entire zoo. So it's 5,000. For the 5,000, we get the spectrum, we compare, and because we tune that, in this case, we get the right guy, also in these cases, and so on. That's how it was generated. And we can regenerate this. They're cached, so we have something like 3 million of these type of things already stored, so we can do it quite fast. Everything was packed in this guy, our lipid oracle, that tells you, what the lipid is. What is important is the following. So, and that's a lesson for the future. I don't think we're trying to replace CID, but the key point is to build on top of CID. It would be great if starting from scratch you can prove it's good, but honestly, that information is there. So building on all of the tools, all of the knowledge that has been accumulated for CID, it's just a smart thing to do. meaning that in the first pass, we go from whatever it is down to potentially chains because we get SN fragments. If you get them, you know where it is. If you don't, you're just going to have your nice underscore and just have the list of chains and neutral losses. But this is something that in AD spectra, but using CID knowledge can be done. And once we have this, or this type of knowledge, that's where, the number was wrong. We basically test all 5,500 isomers. And all of them get a spectrum, and then we match, we rank, and then what we do is we sort of take only the 1% of the top candidates. So it's important you don't stop at the first one. Because sometimes you have missing data, the software might not even tell you where the double bond is. So it could be that 2,000 candidates all have the same score. So just stopping on the first one because you got one hit is not the way of saying that spectrum indicates that the double bond is here and there. So we test all of them, we just have this score, and then we still tape the tip of the iceberg. There's an arbitrary cutoff we use now most of the time, which is, I think, 1%. So we take the best score of all, we take 1% of that, and then all of these guys, it gives a sense on how, it's not confidence, but what is the uncertainty we have on assigning those double bonds. If its spectrum is not so good, you might get something like this. If you aggregate 22 carbons, 6 double bonds, and then for every position we get sort of percentage just by counting the frequency. The software is there. I have to say everything was packed in the software, in the paper that we submitted. Fun fact, it was rejected, and they told us we should go to a proteomics journal. So I'm not sure that the editor actually read it, but it's submitted again, we'll see. But the software is there, it's not nice, it's a Docker. I don't like GUIs, I like things where you put parameters, it runs, it gives you answers. Does it work? I show you the examples. This is an easy one. And then it's going to say, oh, easy, it's just this guy, I'm sure, and there's no uncertainty. You have something which is more difficult, and this is now not 20 minutes runs, it's 100 milliseconds of acquisition of these guys. This is a real spectrum, and then for double bonds, it's 1,365 isomers. These are the ones that match. And typically what you see is actually, not in this case, but it's most frequently it's the first double bond close to the head group that is the most difficult, because that's where you have only one signal to sort of associate that. And that's also where the oxygen, they start having a role in the intensity. So it's really that one which is nasty to find out. But sometimes you have overlaps, it's chromatography, the other things might collude, chimeric and so on. And then it might be that some of the guys are just not really so signed properly. But the idea is to be honest and say, this is the spectrum, this is how much I can tell you. I did my best, decide what you want to do. Having this allows us to really measure sort of how fast we can run something. And the orange point is what we show for these standards. We can actually starting from 500 milliseconds acquisition, or we're discussing the time of acquisition. And typically, if you go down to 30 milliseconds, okay, for one double bond, it's easy. You always get it right. And then if you go to 30, you start seeing that sometimes it's not so great. In other cases, like 4 and 6, you never really get the top because you have the other chain overlapping. So again, if you're just after double bonds, use UVPD, use OzID, use techniques that are specialized for that and much better. EID can do this, but it's not the power of it. It's going through the molecules. But now with the new instrument, actually, we can even go faster. So on average, we can be down to 10 milliseconds of EID accumulation time, and we can actually get this information. That's the coolest thing I can show you today. Tomorrow I have all the cool stuff. This is literally taking a lipid, natural sample, so lipid extract. We buy pretty much anything you can buy from Avanti, we mix it, and we inject it. Okay. And then we do chromatography, and we do DDA EAD, and here the time is 15 milliseconds. So again, we go from 20 minutes on standards in 2015, and now we can do it 15 milliseconds. And clearly you cannot annotate all of the lipids, but the color is not the class, the color is what type of information we found for that specific guy. And green and yellow are things where we can actually have the fragments that tell us something about SN1, SN2. The orange ones are the ones where then we also, doing these things, we find it enriched in some of the positions. I can zoom in some of these guys, and these are really, with 50 milliseconds, honestly, it's amazing. I didn't believe it when I did it, but that's the spectrum we get, very noisy, but that's, coming back to the centroiding, that's where it plays a role, and that's the matching. It is not great. In this case, if you have 3 double bonds, it's an ISO 23, but still there's one match which is much better than anything else, which is this guy. Another example, this is, a 36-1, and we have 2 chains overlapping, and also in this case, it's basically saying, I think it's this one. I will never take this for granted, but another case is down here with the PC, and here you see it thinks that it's one chain, it's 9, the other one is 4, 6, 10, and it doesn't really know. It's sort of uncertain. But, we go from 20 minutes down to 50 milliseconds per thing, and I think this is amazing, and that's where we are right now. Good. So overall, I think it's solved. We can do well. We understood how to do it. It's an empirical model, but it's good enough. Anyone that has an idea to improve it, come to me, because there's always more difficult cases. We are expanding this also, already done, but account for oxidation. Since we generate this library, we also can add at any position oxygens. The beauty of the problem, and we don't have the solution yet, but we're working on this, is how to avoid this combinatorial explosion. Now with double bonds, you already have a lot of things, and if you think of adding even oxygens and peroxides everywhere, so we're sort of trying to become smart in how to address this. Again, if you have ideas, interest, or samples that you probably have some lipid oxidation and so on, because we're using everything, but please come to me. Good. Okay. What about nonlinear lipids or non-lipids? This is basically where we want to go. And I don't have the solution. I have one, which is, let's use Sirius, but we can do better. So that's an example. I have to say we have done not enough, but that's a steroid, and we analyze out of steroids, and that's a steroid where you start doing CID, 35 electron volt in this case, not it's kinetic energy. So it's 35 collision energy, and there is no EAD on top. And that's the same compound doing EAD. The beauty is that if you start doing things together, that's where I think we might be going, when you do at the same time collisions, and before we are basically activated with you start actually getting also shift of spectra. So that's one aspect, I think, not just running in parallel, but potentially combining. I can tell you that there is some stuff that we can start seeing, and it was also going back to some of the discussions we had before that, Brandon was bringing in with the activation. I think we're just exploring this, but yeah, that's having multimodality on the hardware side. I'm all for it. The other thing which I think is not really explored is how much information is a hidden fragment. And, we can take all of these EID spectra and run them to Sirius. It works beautifully for a number of reasons, because it was trained on pretty much every molecule and so on, but I still think that it's not really making a lot of use of the small guys, because typically they're also removed in the processing. But what you've seen in lipids and the things is that there's information down there. We typically don't look at it because we think it's grass. But I think we have to go back to square one, cleaning that up properly, getting also that information and see whether we can get more information. Because so far we have been only looking at the big guys, but you can quote me in this, we can make a bet in 5 years from now. I think down there's more information. Because some of these bonds, carbon-carbon, carbon double bonds, they break, but they're not the most abundant ones. There's always stuff that is breaking around it. So being able to spot them, I think might improve our capacity to distinguish some of these structures. It's work in progress. This is actually an example where we have 140 steroids. This is sort of the playground, the sandbox right now. And we run different adducts. Here is only protonated here. We didn't, but I have much more. It was not fitting. And we are doing both. We are doing CID, we are doing EID, we're combining. And we get different type of classes and so on. So the exercise right now is identifying classes of compounds where we have a lot of isomers, a lot of combination, we have few standards, where we can really find out, okay, how do we best combine electron-based dissociation and CID to also potentially develop the tools. And if the difference between left and right is one case, it was the spectrum, we did a logarithm transformation that basically brings up all of the small guys, and even if you do the same sort of matching, similarity and so on, you start seeing different structure. I don't have the time to go into that, but these are things we're doing. The problem we have is that all of the cool things that we use currently for CID somehow they will build or they use the sheer amount of data that was accumulated by the community, over the years. We are all using the NIST in some way, Mona Mass Bank, all of these libraries out there. Thomas library that was also, acquired by Corina, thank you. I'm getting old. All of them require this large amount of data, either because for the library searches or because they were trained on that. On EID, you're not yet there. And that's why the question is, how can we cut corners? How can we potentially for EID and UVPD come to a point where we can just use those tools equally efficiently? We are doing this works. I think it could do better if you start providing more information and so on. And again, we are colleagues in crime with the group of Sebastian Böcker, who's trying. And and the question for us is really identifying how to do this better, or potentially how hard to CID and so on, without potentially having to retrain everything, all of the fingerprints on EID. But this is a work in progress, and it's cool. So how do we improve there? And these are again my 2 cents. I think moving forward, I think we really have to build on CID. It's never going to be UVPD against or EID against. It's really combining those modalities. And we can run those things in parallel, and instruments allow you to do that. I think there's much more power in combining them because I've seen that the yields, the type of fragments, are just more granular. I don't have too many examples to show you today, but I think that's very important. So, and that is also a call for vendors to allow more of that, to basically combine those things. It might also save a bit of time because you don't have to inject the same samples twice. Being able to run basically in the same things, different modality would be great. And if you ask me, the strategy, the same that we use for the lipids is use CID to get your list of candidates. And it can be 1, can be 10,000, doesn't matter. You just take all you can from the CID. And once you have this list of structure, the idea is to use EID to re-rank those and find those that are more plausible. But then you do this in a space of structures, which is more limited. You're not fishing in the infinite pond of all of the PubChem or something like that. For lipids, we're doing this. We do first CID, and once we want to get the double position, we just basically sample in that limited space. And that makes it numerically, also computationally more feasible. And we are not missing out information. There's more complex stuff that one can do, and I hope I can present more of this next year. But I think the key is not to antagonize, it's really to build on these different modalities. We need more libraries. Internally, Michael and in his lab, they're running 1,000 compounds. We also have done 4,500 compounds, different polarities, energy, and so on. It's just a drop in the ocean. That might start to learn and test a few things. I think we could also do UVPD in a large scale. So if anyone is interested in contributing, help, and so on, we are limited by chemicals, not by instruments. But if someone has chemicals plated, not individual vials and so on, I'm happy to discuss around, because we need to have different labs generating those things. And I will super happy to do UVPD, do EID, combine everything. If you have the chemicals. So this is more of an invitation, because I think we need to get there. And whatever we're going to do, it's going to help. It's going to be the solution, but it's going to help us to build a case, also to convince vendors that there's more potential. And again, we saw that there are 3-4 vendors that offer some of these opportunities. So I think this is going to be very important in the future. And my last point is, I think we have to go back to fundamentals. I'm probably going to regret what I'm going to say now, but you can always run machine learning, but I think some of that stuff we're showing, it's in the space between electrospray or CID and then EI. There's a lot of knowledge out there, which typically is not at its conference, but chemistry, mass spec people, they've seen this stuff a lot in the past. And I'll show you what my rock star is at the moment. It's this guy, who was already mentioned. So I was a few weeks back at SMS, and I know this Gerard Hofgarden from University of Geneva, and he was totally happy to say, this is my last poster SMS, because I was going to retire in 2 months. And I had to zoom in, because the title is Multimodal Tandem Mass Spectrometry for General Screening of Drugs. a lot of people out there that are doing metabolomics specifically are doing a lot of this. And he's doing CID, EAD, UVPD combined, is investigating the mechanisms behind radical cation formation, fragmentation, and so on. There's a lot of knowledge out there. So I think being able to engage with people that really have much more clue than me, for sure, it's important, because that might help us understanding. I'm not saying to do rule-based things, but sort of, go in the right directions to understand what's going on. That's why getting these people engaged, and I know this guy is, the fact that he's retiring helps, because I can invite him to Zurich frequently. It's going to help a lot, but we need to have more of these experts out there that might not be metabolomics, exposomics, hardcore practitioners, but they have the knowledge to help us on that. So that's, if you have a buddy next to you, Department of Chemistry, that might be doing these type of things now for their lifetime, get them on board, because we need that type of expertise. With this, I'm done. Thank you very much. I'll take any questions, but let's maybe open up to any type of comments for everyone.
Any questions for Nicola? I guess this will be a hardcore chemistry question.
Can you help?
It's going to be you've done all of this on the xenotrophes. So, correct me if I'm wrong, what happens if you now combine this with ion mobility to really start to separate out these isomers?
I don't know.
Because the more you can separate, either on chromatography or in the gas phase before you start fractionating or breaking them apart, the more likely you are to be able to figure things out. So maybe our SciEx friends need to get with MobileIon and do that connection, or the rest of you use the Bruker Omni.
So you're talking to a biologist.
Yeah.
I think all of that happens before. All of our mobility you see happens in the front of any collision cell and so on, unless you have some other waters and so on. So I don't think this is so easy to be implemented. But let's, who builds that instrument, we can have a look. What I think is going to be more crucial or more cool to have, it's spectroscopy to really identify some of these fragments in there. And there's some groups working on this, not for metabolomics, but I think David Wisher was here, right? It was one of these really cool papers where they show that the mechanisms that we depict are actually different in reality. So having that type of information, which is really orthogonal, I think that might help us to understand more about this.
Yeah, well, I started as a chromatographer, so I tend to think before you do any sort of mass spec, the cleaner what you're looking at, the more able you'll be able to interpret it. And I think we have the instruments to do it. They just haven't been put together yet.
Yeah.
So
sometimes it's about the time that you want to invest for a single sample. It might be the cost, where you want to be fast in the chromatography. And then you take into account that they might have overlaps, chimeric spectra. It's a nature of things. And but we have to talk to Lyon.
So has anybody done scanning EAD yet?
Can you elaborate? Scanning EAD?
Yeah, so you talked about different energies. So each molecule might require an optimization.
Right.
But if you're running in chromatography time, where compounds are coming at you at different speeds, they may have different optimal EADs.
Totally,
so would you be better off having a scanning one so that you can
So basically testing...
So rather than doing it on each sample, one at a time, have a scanning process, and now you get...
We have not done that yet thoroughly. We're basically running a fixed energy for the entire run, and then we inject several times. I'm not sure what is possible on the hardware side, but we definitely are using different energy. And what I'm not saying now, we can go to much higher energies. So the steroids, if I use 12 on the lipids, 12 is not even scratching them. So we have to go much higher, and now we can start doing this. But whether down the road the best way is going to be to ramp or to step in the same run or rather than inject, that's going to depend a bit on the technical aspects, and we'll see.
Okay, best of luck.
More questions, please? We still have 15 minutes to fill. Yeah.
Yeah, a short one. I don't know how much it will fill. Congratulations, Nicola. Great tool for the community. Was there any is there any room for DIA experiments rather than ramping up the energy, or using one energy but going around to increase the noise, decrease the noise level?
So you're asking whether one can do data independent acquisition with EAD? So, theory, yes. In practice, yes. I think DIA, and that's what I'm going to present tomorrow, it's become so fast on CID that I don't think you have physically the time to do that. But maybe next year I'm going to tell you the opposite. I don't know.
All right. Thank you. Looking forward to that.
Hello. Thank you for the presentation. And in the contrast of previous question, is there any way to characterize and quantify correlated isomers correlated in one chromatographic
Yeah,
peak?
so that's what we call chimeric spectra, and that's why I was saying sometimes it's really important to just try all possible candidates to see that. I don't know how well that works. I mean, this is a big topic. I don't think we address it as a community properly. I don't know, probably, I don't want to point to anyone, but there's people in this room that might have a stronger opinion on this. It remains tricky, and you have to be lucky, and you have to see, but I think that's important that we start dealing properly with chimeric spectra, particularly as we do if you do things fast, because you are not patient, and then it's the nature of things. But we see chimeric spectra if we do half-an-hour gradients, and if you do 2-minute gradients, we always see them, so it's, there's a chromatography has some limits, and you don't solve all of this. So dealing with chimeric spectra, it's essential to move forward.
So actually they did it for the C5 acyl carnitine. So they checked different mixtures of the two standards, and you can titrate this out actually. That you can, based on the fragment ratios, you can get this. But this is a very selected sample of just 2 isomers.
Thank you.
Alex.
Hello. Thank you for an excellent talk. Just a question following up on that, actually, on the chimeric spectra issue. Have you tried running this through some of the older sort of GC algorithms for trying to resolving the chimeric spectra and that sort of thing? Because I think a lot of the times in LC we forget that we did a lot of work in GC trying to resolve this multi-fragmented...
Yes, and that does not work.
Okay.
And that's exactly the things we do in DIA. And the problem is, think of lipids. The phosphocholine, the main fragment is 184. As soon as you start using time, like ESCs or TS-insons to resolve the pure spectra of any compound, the first fragment you lose is 184. And that's why usually for many classes of compounds, using that information, whether you use the MDIS or parafac, whatever you use, you lose that guy because it goes up and never comes down. It might work for some samples. What we try with lipids, what we tried with all the type of things, we lose quality. That's why we don't really go that way. But it could be that it's because we are running faster gradients.
Yeah.
But I would advise against any of type exercise like that, because in our hands it never worked. Okay. So who wants to fragment stuff differently? I mean, this is the question.
Important. Plate it. Don't send him epis, send him well plates. Nobody? Any general questions? We're still here. Otherwise, catch you over coffee, beer, hard stuff. The answers might be not that scientific then, but... Okay, thank you
very
for
much
being
for coming.
here. Have fun.